Electricity and current. In this lesson, we're going to be talking about what electricity is, atoms and electrons, static electricity, current electricity, drawing circuit diagrams, parts of an electric circuit, the cell, open versus closed circuits, electric current, circuit types, and then we're going to end with Coulombs. Electricity. It's enlightening. So I want you to pause the video and I want you to think about these 4 questions. First of all, what is electricity? Where does electricity come from? What do we use it for? And how would your life be different without it? So again, pause the video and answer these 4 questions. Make sure you write them down. Electricity. Everything in the world is made up of atoms. Each atom is made up of smaller parts, and one of those parts is called the electron. The electron is located on the outside of the atom. And it's the electron that's going to be really important in electricity. Electrons are negative particles which can move from atom to atom. When electrons move quickly from one atom to another, it's called electricity. So if you have another atom over here, so let's draw another atom like that. I'll draw some electrons over here. So if we do take our electrons and we move them from here to here, that movement of electrons is called electricity. Now we're going to be dealing with 2 types of electricity, current and static electricity. First up, static electricity. Static electricity is the charge that stays on an object. These charges are usually created through friction. Charges can jump from one object to another, like we see with lightning. And other examples include static shocks, hair standing up on end. All these things are due to static charges being built up on objects. In terms of lightning, you're going to get a large buildup of electrons up in the cloud, and then all those electrons are all at once going to jump down to the slightly more positive ground. Current electricity. The other type of electricity that we're going to talk about is current electricity, and this is the type of electricity that's used in our homes. Current electricity is a steady flow of electricity that moves along a wire or path called a circuit. Circuit just simply means to go around. When we're talking about circuits and current in general, we need to think about what path those electrons are traveling along, and that's where our circuit diagrams come in. We call them schematic diagrams, and they're connecting wires drawn as straight lines at right angles to each other, which show the path that the electrons take from one point to the other. They start at a power source like a battery or a wall plug and end back at that same wall plug. Circuit components are symbols, which are simple and usually look similar to what's happening. Parts of the electric circuit that you're going to be familiar with, that's going to be our wire, so our connecting wire. Here's a picture of it on the right hand side. A light switch, drawn like this, but usually seen like this. A toaster, so it's going to be drawn like that. This is the real picture of it. So that's, in more general terms, is going to be a resistor or a load. And then a battery. So a AA battery would be an example of that. And this is what it's going to look like in your model building kits. Other things we have cells. So a cell is similar to a battery. You can see our battery right here. Okay, so it's very similar to our battery, except it only has one of these big guys and a small guy. A light bulb. Now I typically draw it simply as an X, just for ease of drawing, and it stands out easier. We have a voltmeter and we have an ammeter. Now this guy right here is actually called a multimeter, and it will measure both voltage and amps. The cell. Now we talked about the cell. 2 or more cells is going to equal a battery. The cell stores chemical energy and transfers it to electrical energy when a circuit is connected. When 2 or more cells are connected, as we just said, we call it a battery. The chemical energy inside the cell is carried by electrons from the negative terminal to the positive terminal, and it's used up as it pushes current around the circuit. So in this case, you're going to have your positive terminal right there. You can see positive, and you're on a different color, and you're going to have your negative right there. So electrons are going to flow from one part of the battery to the other. They're going to go from the negative to the positive. So our electrons are going to go like this. Now you'll learn later that current actually goes the other way, but electrons are going to flow from the negative terminal to the positive terminal. And it's this movement of electrons like we were talking about that allows us to have electricity. Now there are many different types of batteries depending on the application. We just showed one right here. This is a car battery. That's going to be your typical AA batteries. There are rechargeable batteries like you find in electric vehicles that can be used over and over again. And then there's one-off batteries like we have in our first picture up here. These are typically batteries that once you use up all the electrical potential energy inside the cells, they're disposed of because they can't be used again. The chemistry inside the battery determines how many times it can be used and how long each charge will last. Another example of a rechargeable battery is the battery found in your device. Open versus closed circuits. A circuit can be described as either open or closed. A closed circuit is when the circuit is operating and the current is flowing. Example of a closed circuit. Now you can see this doesn't look like a typical light switch, but what you'll notice is that if there's a wire coming in this way, the electricity can flow through the wire, up the metal, it can join to this metal, come back down, and go out the other side. So this is a connected closed circuit, and electrons can flow, the light will be on. An open circuit, as represented right here and right here, you can see that the electrons can go in, they can go up here, but they can't get to this side right here. So since there's a break in the circuit right there, the electrons can't flow and the circuit won't be on. In this case, the light will be off. So what is an electric current? An electric current is a flow of microscopic particles called electrons through wires and components, like we've talked about. The electrons flow from the negative terminal to the positive terminal of the cell, but current runs in the opposite direction. So I did touch on this. Electrons are going to go from the negative terminal, around in this blue line right here, back to the battery, whereas current runs the opposite direction. So that's going to be represented by the green arrows. It's going to go from the positive terminal around the circuit and to the negative terminal. Now there are two main types of circuits. There's a series circuit, which only has one path. And that's how you're going to know that it's a series circuit. It's going to have a single path for the electrons to travel. And you're going to have parallel circuits, where there's going to be more than one path for the electrons to travel on. So series circuit, let's break them down a little bit further. In a series circuit, the components are connected end to end, one after the other. You can see that this light bulb is connected to this wire, which is connected to the light bulb, which is connected to the battery, and so on, one path. They make a simple loop for current to flow around. If one bulb blows, it breaks the whole circuit and all the bulbs go out. So if we were to somehow take this bulb out, like it stopped working or it was removed from the system, there'd be a break in the current, and we wouldn't actually be able to get from one point to the other. In parallel circuits, the components are connected side to side. So you can see they're connected in parallel to each other. There's one path here the electrons can take, and there's another path here that the electrons can take. So in this case, the electrons have a choice of routes, and if one bulb blows or one branch is taken offline, the electrons can still travel this way, and this bulb can still work on the bottom. A funny story, Christmas lights used to be made using series circuits, and if you watch an old movie, you'll find that the big running joke about putting up Christmas lights is that if one bulb goes, the whole tree or house goes out, and they have to check each bulb to find out which one was the culprit. Now Christmas lights are made using parallel circuits, so each bulb is connected in parallel, so if one bulb goes, the whole strand doesn't go out. Key term, current. The flow of electricity around a circuit is called current, and it runs from positive to negative like we've talked about. Now we abbreviate current to I, so we would say that I is equal to 1 amp. So I is going to represent current. And it's the amount of electrons passing a given point every second. Coulombs. 1 amp is the amount of electrons passing a given point in 1 second, like we just mentioned. 1 amp equals 1 coulombs per second, or 6.25 times 10 to the 18 electrons per second. So to get 1 amp, you need to have 6.25 times 10 to the 18 electrons passing a given point. Let's think of it like a turnstile, like you see in an event. So you need to have this many electrons passing this point every second. And if you do, then that equals 1 amp. If you have 2 times that amount, then you'll get 2 amps, and so on and so on. Therefore, if the current flowing through a wire, toaster, or hairdryer is 1 amp, you're going to have 6.25 times 10 to the 18 electrons flowing past that point every second. Check your understanding. I want you to pause the video and I want you to answer this question. How many electrons pass a point every second if the current is 2 amps? Keeping in mind that 1 amp equals 6.25 times 10 to the 18 electrons passing a given point every second. Okay, got your answer? So if 1 amp equals 6.25 times 10 to the 18 electrons per second, and we have 2 amps that we're looking at, we're going to multiply this number by 2, and we're going to get 1.25 times 10 to the 19 electrons per second. This symbol here, by the way, represents our electrons. Second question. How many electrons pass a point every second if the current is 12.6 amps? So let's write this one out. This one's a little bit more difficult. So I is going to equal to 12.6 amps. That means that 12.6 times 6.25 times 10 to the 18 electrons pass a given point every second. So how many electrons pass a given point every second if the current is 12.6? Well, our answer is going to be 12.6 times 6.25 times 10 to the 18, which is equal to 7.88 times 10 to the 19 electrons per second. Third one, what is the current? So I is the question. If 3.125 times 10 to the 18 electrons pass a point every second, 3.125 times 10 to the 18 electrons per second pass a given point. We know that if it was 1 amp, it would be 6.25 times 10 to the 18 electrons per second. So we write 6.25 times 10 to the 18 electrons per second, and then we'd say per 1 amp. You're going to take this number here, 3.125 times 10 to the 18, and divide it by 6.25 times 10 to the 18. And then you're going to get your answer in amps. Now, a bit of a trick you can do, since they're both times 10 to the 18, you can actually get rid of the times 10 to the 18 in this case. If one was times 10 to the 19, you wouldn't want to do that. You'd have to do some other math manipulation. But in this case, since they're both times 10 to the 18, you can just get rid of both. And when you divide those two out, you get 0.5 amps, which makes sense. Since 3.125 times 10 to the 18 is half of what 1 amp requires, it's 0.5 amps. And that concludes our lesson on electricity and current.